Hi students, good morning. Welcome back to our physics classes. And during the last classes, we have defined Ohm's law and we have seen the properties of resistance, resistivity in relation with Ohm's law. And we have seen that resistance is the property by which a material offers hindrance to the passage of electricity. And Ohm's law says that resistance is a constant provided the physical quantities of a conductor remain same. That is, physical situations remain same. Such like temperature. As temperature changes, resistance also changes. So how resistance changes with temperature? See, resistance and resistivity both are the properties of a conductor. But resistivity is the property of the material of the conductor and resistance is the property of conductor. That means it depends upon the dimensions of the conductor. But resistivity is independent of the dimensions. It depends only upon the nature of the material of that conductor. But resistivity and resistance both varies similar in accordance with temperature, which means how temperature varies with how resistance varies with the temperature, the same way resistivity also varies with the temperature. So if you are defining the relation between resistance and temperature, remember that is same for resistivity and temperature also. So we can see how resistivity or resistance changes with temperature. Okay, so we can continue with our current electricity, and now we have to see how resistance or resistivity changes with temperature. So here we are defining the relation between resistance and temperature. And we have already know or we have already derived the resistance R is given by M divided by N E square tau into L by A, from which M by N E square tau is resistivity and L by A. L is the length of the conductor and A is the area of the area of cross section of the conductor. From this relation, it is clear that R directly proportional to 1 by tau. That means R inversely proportional to tau. What is tau? Tau is the relaxation time. What is relaxation time? Relaxation time is the time interval between two successive collisions of an electron with the positive sides. Actually, that collision with the positive sides are hindrance. That positive sides collision with the positive sides are actual hindrance of the movement of charges through a conductor. So R proportional to 1 by 2. That means when the relaxation time is less, resistance will be more. Relaxation time is less, resistance will be more. We will come to that point. For that, what is tau? Tau is relaxation time. Relaxation time is the time during which the electrons moving with the velocity, drift velocity, which means it is the time duration which the electron travels through mean free path. What is mean free path? Mean free path is the distance traveled by an electron between two successive collisions. So lambda is the mean free path. Vrms is the velocity with which the electron is traveling through the conductor during the time tau. So we can say tau is equal to lambda by Vrms. That means time is distance by velocity. So since tau is equal to lambda by Vrms, 1 by tau will become Vrms by lambda. So when you are comparing with the above equation, lambda is equal to or R proportional to 1 by tau, So tau is equal to lambda by Vrms. So R proportional to Vrms divided by lambda. So Vrms, last year we have seen in thermodynamics, Vrms is directly proportional to root T. What is T? Absolute temperature. So as T increases, Vrms increases. See, as T increases, Vrms also increases. Hence, when Vrms increases, R also increases. As T increases, R increases. Did you get the idea? See, R is directly proportional to 1 by 2. But tau is equal to lambda by Vrms, or R proportional to Vrms by lambda. But Vrms is proportional to root T. As T increases, that implies as T increases, Vrms increases. As Vrms increases, which in turn R increases. So we can say that as T increases, R increases. Which means as the temperature of a conductor increases, its resistance increases. As temperature of the conductor increases, its resistance also increases. From the first equation itself, you can infer that. What is that? R proportional to 1 by 2. When tau increases, R decreases, or tau decreases, R increases. What is tau? Tau is the time between two successive collisions. If time between two successive collisions increases, time between two successive collisions increases means between two collisions more time is required, which means number of collisions are less. If the number of collisions are less, less hindrance is offered, which means resistance will be less. If tau is less, which means relaxation time is less, between two successive collisions there is no such a large time interval, which means number of collisions are more. If number of collisions are more, hindrance will be more, then resistance will be more. That is the condition. So anyhow, we can see that as the temperature increases, Vrms increases, which in turn tau decreases, then R increases. Anyhow, as the temperature increases, resistance increases. As the temperature increases, resistance increases. See, at 0 degrees Celsius, then we can have a relation between temperature or we can show with a mathematical expression how resistance varies with the temperature, absolute temperature. See, at T equal to 0 degrees Celsius, the resistance will be R0. And at T degrees Celsius, resistance will be RT. Therefore, RT is given by an equation R0 into 1 plus alpha T. RT is equal to R0 into 1 plus alpha T. You know, R0 is equal to resistance at 0 degrees Celsius, and RT is the temperature at T degrees Celsius. And remember, that is small t, 1 plus alpha T, that is small t. So RT is equal to R0 into 1 plus alpha T. Alpha is temperature coefficient of resistance. Alpha is the temperature coefficient of resistance. So from that equation, RT minus R0 is equal to R0 into alpha T. So alpha is equal to RT minus R0 divided by R0 into T. That is RT proportional to T. Which means as the temperature increases, resistance increases, and alpha is equal to RT minus R0 divided by R0T, where RT and R0 are the resistance at temperature T degrees Celsius and 0 degrees Celsius, and alpha is the temperature coefficient of resistance. See, this we have defined for resistance. RT is equal to R0 into 1 plus alpha T. If you are writing this equation for resistivity, you can follow the same pattern. Resistivity is denoted by rho, you know. So rho 0 and rho t are the resistivity at 0 degree Celsius and t degree Celsius. Then rho t is equal to rho 0 into 1 plus alpha t. Alpha remains same. Alpha is the temperature coefficient of resistance. Rho t is equal to rho 0 into 1 plus alpha t, where alpha is the temperature coefficient of resistance. So that is the relation between temperature and resistance and temperature and resistivity. So we have seen the fourth factor that can affect the resistance. So we have already seen three factors that can affect the resistance of a conductor, that is resistivity, that is material, then length and the area of cross section. Now the fourth factor that can affect the resistance of a conductor is its temperature. So temperature and resistance is directly proportional. As temperature increases, resistance increases. As temperature decreases, the resistance decreases. Okay, so we have defined resistance properly now. And what is resistance? What is the property of resistance? Resistance is hindrance to the current flow, which means if you provide resistance in a circuit, suppose if you are providing resistance in a circuit, what it means, current finds difficulty to flow through that circuit. For a circuit, if the resistance is less, what it means, current can easily pass through that circuit. So resistance determines the current through a circuit. Resistance determines the current through a circuit. If the resistance present in a circuit is less, then more current will flow through that circuit. If the resistance present in the circuit is more, then the current through that will be less. Hence, if you want to reduce the current in a circuit, what to do? You have to increase the resistance in that circuit. Or if you want to increase the current in the circuit, you have to decrease the resistance. And if you want to decrease the current in the circuit, what to do? You have to increase the resistance. So practically, in nowadays you are using different circuits, electrical circuits, and in practical electrical circuits, we are using resistance in the form of carbon resistors. In many of the electrical circuit, digital electronic circuit especially, we are using resistors in a form of carbon resistors. So in market, carbon resistors are available. Electronic market, you can find, you can buy carbon resistors, and these carbon resistors has its own particular values. And I will show you a carbon resistor. See, this is a carbon resistor. So in this carbon resistor, nowadays these kind of resistors are used in electrical circuits, and carbon resistors are having different resistor values, and their resistance values are given by the different colored rings. All we can say that the values of carbon resistors are given by this color code. Values of carbon resistors are given by color code. So what do you mean by color code of a resistor? Color code of a carbon resistor. See, this is a carbon resistor. On this carbon resistor, you can see 1, 2, 3, 4 colored rings. See here, 1, 2, 3, 4 colored rings are there. Okay, and each color has its own value. See here, you can see one table here, and in this table you can find different colors: black, brown, red, orange, yellow, green, blue, violet, gray, and white. So these are the colors which is used for making rings over a carbon resistor. Okay, so on each carbon resistor you can find this kind of colored rings, and these colored rings are of these black, brown, red, orange, yellow, green, blue, white, gray, white. Any of these 10 colors. These rings are made up of any of these 10 colors. And each color has its own value. Black is denoted by 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, violet is 7, gray is 8, and white is 9. Okay, so this is the sequential order of these colors and the corresponding numbers. Black, brown, red, orange, yellow, green, blue, violet, gray, white, and they are correspondingly given the values 0 to 9. Now you see here these three rings are close and the fourth one is somewhat far away from the first three. Okay, so you keep all these three set of colors in the left hand side and the last one in the right hand side. And you see the first colored ring, that is the first digit of its value. See, the number of first colored ring is the first digit in its value. Number of the second colored ring is the second digit in the value. Third one, color of the third is multiplier. Multiplier means it is expressed as a power of 10. It is expressed as the power of 10. And fourth one is tolerance. Tolerance means expected variation in the value of that particular carbon resistor. Means it's a mechanical system. It's a device, and there may be some variation in its expected value, and how much variation is expected, that is given by tolerance. So first three colored rings are there. First one is the first digit, second one is the second digit, and third one you are expressed as a multiplier, that is the 10 to the power 10 to the power, and fourth one is tolerance. See, generally the fourth ring may be of silver or gold or no color. No fourth ring will be there. If the fourth ring is of silver color, that indicates plus or minus 10 percentage of variation. Plus or minus 10 percentage. That means but 10 percentage may increase or 10 percentage may decrease. And if it is a gold ring, that will give the plus or minus 5 percentage of variation. That means 5 percentage increase or 5 percentage decrease. And now we can see how you can find the value of that carbon resistance using color code. See, in the same, first one is of yellow. So its value you can find from this table. So yellow is number is 4. So see, yellow is denoted as 4. Second one is, which one is second? Second one is violet. So violet's number is 7. So that is the second digit which is denoted as 7. Third one is red one, and it is expressed as a multiplier. That means 10 to the power 2. 10 to the power 2 means 100. So red number is 2. It is expressed as 10 to the power 2. That means multiplied by 10 to the power 2. That means multiplied by 100. That is multiplier. So 47 into 100. Are you getting me? 47 into 100. And fourth ring is tolerance, and it is of gold. Gold is plus or minus 5 percentage. Gold is plus or minus 5 percentage. So what will happen? Its value is 47 into 100 ohm. 47 into 100 ohm. That is 4.7 kilo ohm. 4 point, see, it is 4.7 kilo ohm plus or minus 5 percentage. It is of the value 4.7 kilo ohm, that is 4700 ohms. with plus or minus 5 percentage of variation we will expect in this value. Is it clear? See, first ring is the first digit, second ring is the second digit, third ring is the multiplier, and the fourth ring is the tolerance. And you have to remember all these colors and their corresponding numbers in the sequential order. Black, brown, red, orange, yellow, green, blue, violet, gray, white. And the numbers are 0 to 9. Okay, so that is the color coding is very important, which means many times it is asked for your board exams. Suppose and you can see what is the color coding of this one. See, the first ring is brown. Brown is 1. You write brown is 1. Second one is red. Red is 2. So 12. Then third one is black. Black is 0. 10 to the power 0. 10 to the power 0 is 1. So it is 12 ohm. 12 ohm, and the fourth ring is gold. Gold is plus or minus 5 percentage. So 12 into plus or minus, sorry, 12 ohm plus with a plus or minus 5 percentage of variation. 12 ohm with a plus or minus 5 percentage of variation. Is it clear? Okay, so that is carbon resistor and its color coding. So you have to remember that colors with its order. That is, I will give you a mnemonics. What do you mean by mnemonics? Mnemonics is a technique to memorize something. Mnemonics is a technique to memorize something. So the problem is you have to remember that colors in its sequential order. Number is simple, that is 0 to 9. 10 numbers are there, 0 to 9. So how you can remember that colors in order? For that I will give you a sentence as the mnemonics. Listen carefully. B.B. Roy of Great Britain have a very good wife. B.B. Roy of Great Britain have very good wife. Did you get? B.B. Roy. B.B. Roy. B.B. is initial of Roy. B.B. Mean B.B. Roy. You can write all those in capital letters. B.B. that is initials B.B. Roy. Roy is a name of Great Britain. Great Britain. G you can write in capital letter. Britain. B also you can write in capital letter. Great Britain have very good wife. V G W, that you can write in capital letters. So I repeat, B.B. Roy of Great Britain have very good wife. So now you see the letters that you have written in capital letters. B.B. that is black, brown. Roy, R-O-Y, red, orange, yellow, of Great Britain. Green, blue. Green Britain have very good wife. Violet, grey, white. Is it easy? Can you remember this sentence? B.B. Roy of Great Britain have very good wife. And the numbers are from 0 to 9. Now you can memorize all those colors in the sequential order and their corresponding number. Remember, first color mean number of first color ring is first digit, second ring is second digit, third color is multiplier, and the fourth one is tolerance. If the tolerance is silver plus or minus 10 percentage, it is a gold plus or minus 5 percentage. If it is no color, that is plus or minus 20 percentage. If there is no fourth ring, the tolerance will be plus or minus 20 percentage. So that is color coding of carbon resistors. Remember, color coding is very important. Sometimes it is asked the color rings are given and you have to find out the value of that particular resistance. Otherwise, particular resistance value will be given and you have to identify which are the colors and in which order they are provided. Okay, so practice it and I will give you the questions in practice time. So remember these colors and the corresponding numbers, that is carbon resistors. Okay, so when you consider a electrical circuit, I already told you in electrical circuit we are making use resistors. Sometimes we have to increase the current, then you have to decrease the resistance. Sometimes we have to decrease the current, then you have to increase the resistance. So anyhow, the resistance you have to adjust with a circuit. In the physics lab, you will come to do some experiments, electrical experiments next year, means this year, not next year, this year. So at that time, we are making use resistance box in circuits. In practical in educational purpose, in practical situations or practical labs, we are making use resistance boxes so as to introduce resistance in the circuit. But in practical commercial situations, I already told you, means carbon resistors are used. Carbon resistors are used in digital electronic circuits nowadays. Okay, remember that. So anyhow, when you want to have a particular value of resistance in a circuit, sometimes with a single resistor you can't achieve that kind of resistance value, just in the case of a capacitor. So what to do, you have to go for combination of resistors. We have already seen combination of capacitors. In that we have made the diagram with the four capacitors in series and capacitors in parallel. You can remember that. Resistance, I mean, series means end to end connection. Resistance means end to end connection. And across connection is parallel connection. And in case of across connection, both resistance and capacitor, the potential across each independent entity will be same. That means if it is a capacitor, potential across capacitor will be same. If it is a resistance, potential across the resistance will be same when they are connected in parallel. And when they are connected in series, in capacitor charge remains the same, but in resistor they can flow through the resistors, so the current through each resistor remains the same when they are connected in series. Diagram is very similar to the capacitors. Instead of capacitor, you have to replace the capacitor with resistors. You know the symbol of resistor, you have already learned that. So in the diagram for combination of capacitors, series combination, parallel combination, you just replace that capacitor with the resistance, so you can make the diagram for series combination and parallel combination of resistors. Okay, you do by yourself that, make the diagrams. We will discuss that cases here. Okay, so we have already said that we have to make the resistors in series or in parallel separately. So we can start with resistors in series. As I already told you, in series, the current flowing through each resistor is same. Current flowing through each resistor is same. But since they are having different values of resistance, potential developed across each resistor will be different. Potential developed across each resistor will be different. So the potential across the first resistance V1 will be I into R1, V2 will be I into R3, R2, and V3 will be I into R3. Suppose three resistors are connected in series. Then R1, R2, R3 are the individual values. So the potential across R1, R2, R3 are V1, V2 and V3. They are given by IR1, IR2 and IR3. But the total potential is V is equal to V1 plus V2 plus V3. So I into R is the net potential, which is equal to I into R1 plus I into R2 plus I into R3. Since current flowing through each resistor is same, R is equal to R1 plus R2 plus R3. What is R? R is the effective resistance of the three. We have already seen that when they are making a combination, the combined one you can replace with a single one with the effective value. If it is a capacitor, effective capacitance. If it is a resistance, that is effective resistance. Anyhow, so R is equal to R1 plus R2 plus R3. Okay, so that is the effective resistance when resistors are connected in series. In series combination, effective resistance is the sum of individual resistances. See, in parallel combination, what happens? In parallel combination, three capacitors are connected in parallel. So the potential across each resistor remains the same. But since they are having different resistors, different resistance value, current through each resistance will be different. Current through the first one will be I1, which will be V by R1. Current through the second resistance will be V by R2, I2. Current through the third resistance I3 will be V by R3. Since the total current flowing I will be I1 plus I2 plus I3, then V by R is equal to V by R1 plus V by R2 plus V by R3. That is 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is, the reciprocal of effective resistance will be sum of reciprocals of individual resistances. That is when the resistors are connected in parallel. Now you can recollect the sentence that I have made when we were discussing about the combination of capacitors. When we were discussing the combination of capacitors, I have already told you, when you are taking the combination of series combination of resistors and capacitors, conditions will be interchanged, which means when capacitors are connected in parallel, C is equal to C1 plus C2 plus C3, and when they are connected in series, 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. But here, when resistors are connected in series, then effective resistance will be R1 plus R2 plus R3, and when they are connected in parallel, 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Obviously, when resistors are connected in series, effective value will be more than the highest individual, and when resistors are connected in parallel, effective value will be less than the least individual value. That makes a difference. Okay, so that is the combination of resistors, series combination as well as parallel combination. It is very simple, you have already learned, and similar one you have defined in the capacitor also. So remember the condition, when they are connected in series, current through each resistor is same, and when they are connected in parallel, potential across each will be same. Okay. So that is the combination of resistors. Suppose you are having a resistor and it is connected to a cell of potential V. You are connected the cell of potential V. And according to Ohm's law, when a resistor is connected to a potential or a cell, there will be a potential difference across the ends of that conductor or a resistor, whatever may be, and current starts to flow through that. Current starts to flow through that. The current flowing is V is equal to, sorry, I is equal to V by R. Current V, I is equal to V by R. So for flowing the current or to move the charges through the current, work should be done. For moving the charge, work should be done. Why work is required? Because there is a potential, and through the potential charges are flowing. To make the charges flow in a potential field, work is required. So if I amount of current is flowing through a conductor through a time t, then how much charge is flowing through? That is q amount of charge is flowing, and I is equal to q by t. Charge flowing per unit time is measured as current. So from the current and the time, how you can find out the charge? Charge q is equal to I multiplied by t. I multiplied by t. Okay, so I will show you. See, the charge flowing q is equal to I into t. So it is, since it is connected to a cell of potential V, the conductor is connected to a cell of potential V. So to move a charge q, how much work is required? Work done will be W equal to V into q. That also we are already, that equation we are already knowing. W is equal to V into q. So V into Q, which is equal to V into I into T. But R is equal to V by I. So W is equal to I squared RT, or W is equal to V square by R into T. If you are replacing V by IR, then you will get I squared RT, or I by V by R, you will get V square by R into T. What is this W? What is this W? Work required to move charges through that conductor. So whenever work is done, that will be stored as energy. So this work done will be stored as electrical energy. This work done will be, this work done is known as electrical energy. So electrical energy is given by W is equal to I square R into T. I square R into T. So I square RT or V square by R into T is the electrical energy when a charge Q is flowing through a conductor through a time t when it is given a potential V, or when I amount of current is flowing through a conductor of resistance R for a time t, electrical energy is generated, that is I square RT. Electrical energy is given by I square RT. From where that energy comes? That energy comes from the that energy comes from the cell. Cell is having chemical energy, and that chemical energy is converting into electrical energy here. Okay, so anyhow, W is equal to I squared RT is the electrical energy generated when an amount of current I is flowing through a resistance R for a time t, or electrical energy V square by RT is generated when a conductor of resistance R is provided a potential V for a time t. That is electrical energy generated. But we know that energy generated per unit time, what is that? That is the power. So power P is equal to W by T. Energy generated or work done per unit time, or energy generated per unit time is work. So sorry, power is equal to W by T. So P is equal to W by T, but W is equal to V into I into T. So P is equal to V into I into T divided by T, that is V into I. Or P is equal to Vi, or P is equal to I square into R. Because W is equal to I square RT, P will be W by T, so I square RT divided by T, that will become I square R. So P is equal to I square R. Two equations for electrical power, that is I squared R and Vi. And the unit of power is watt, and the unit of energy is joule. That no problem, no doubt about that. So 1 watt is equal to 1 volt into 1 ampere. From that equation, P is equal to Vi, P measured in watt, and voltage is measured in volt, and potential is measured in volt, and current is measured in ampere. So 1 volt into 1 ampere is equal to 1 watt. Okay. But the commercial unit of electrical energy, that you know, because every month you are paying for that. In your house, you can find a electrical meter. Nowadays, it is all these meters are kept outside, and that meter reads the usage of electrical energy in our house. But that meter is known as watt hour meter. That is known as watt hour meter. Anyhow, it is measured as watt hour. It is termed as watt hour meter, electrical meter. It measures the electrical energy. It measures the electrical energy used in our house. That is the rate of usage of electrical energy. That is power, electrical power. So in that, we are defining another unit called unit. Means in the electricity bill, you can find how many units you have used in this month, and per unit how much you have to pay, therefore how much you have to pay total. In that way you can find the electricity bill. So what do you mean by the unit? The unit is 1 kilowatt hour. Unit is 1 kilowatt hour. 1 kilowatt hour is equal to 1000 watt into 1 hour. 1000 watt into 1 hour. That means usage of electricity or usage of electric power at the rate 1000 watt in 1 hour. That is known as 1 unit. 1 unit is the usage of electrical power 1000 watt, that is 1 kilowatt in 1 hour. That is 1 unit. So 1 kilowatt means 1000 watt multiplied by 1 hour. 1 hour means 60 into 60 seconds when you are converting into SI units. So 1000 into 60 into 60, which means 3.6 into 10 to the power 6 joules. So 1 kilowatt hour, that is 1 unit, is equal to 3.6 into 10 to the power 6 joules. 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joules. Okay, so that is the commercial unit of electrical energy and electrical power. So electrical energy is given by electrical energy is the energy generated when a current is flowing through a conductor. If I amount of current is flowing through a conductor of resistance R for a time t, the electrical energy generated will be I squared RT, and the electrical power consumed will be I squared R, or VI, or V square by R into VI into T, or V square by R into T. Power is VI I squared R, or V square by R. Different equations for electrical energy and electrical power. Okay, so that's all about electric energy and electric power. So here during this session we have seen how temperature affect the resistance and resistivity, then combination of resistors, its series combination of parallel combination, then a special kind of resistors called carbon resistor, and its color coding, it is very important. Remember that B.B. Roy of Great Britain have very good wife, and electrical energy and electrical power. So that's all about the chapter current electricity. So we have finished one unit, electricity. Electricity, static electricity we have seen, that is electrostatics we have seen. Then current electricity we have seen, electricity. And see, here we have talking about the properties of charges and the properties of charges at rest and the properties of charges under motion. So, during these two units, that is electrostatics and current electricity, we were discussing about the properties of charges. So, I think you have already learned the concept that we have discussed in the electrostatics. Now, we concluded a current electricity also. So, problems I sent to you, you have, I think you have already gone through that and solve other problems in the numerical copy. And as I already told you, if you have any doubt, you can contact me through WhatsApp, and I will give you the solutions for those questions. Then be up to date. And then we have completed our two units, electrostatics and current electricity. Then the next chapters, next unit we have to, next session we have to start with our new session or new section of our syllabus, that is magnetic effect of current. That means we have seen the static properties of charges, then dynamic properties of charges, then that is the another property of a dynamic charge, that is magnetism. So magnetic effect of current. Anyhow, keep well and be safe at home. We will meet in the next class. Bye.